This tutorial is about how to apply UDF, some explanation to UDF, and how can we apply um, a variable boundary condition on a 3D body using a UDF. So this is a very simple cylindrical geometry which is representing a pipe. So I'm taking a problem similar to when we apply solar irradiation, let's say, or temperature. If you want to simulate something when you have a solar receiver or collector, something like that, a tubular receiver. So this is just a tube, fluid body. So what I did is I just have sketched this circle, extruded it, and that's the body. And then I changed the type to this part body to fluid body. Okay. So after that, here comes the mesh. So I created a very simple mesh with a body sizing of 1 millimeter. My cylinder height is this one. I took a random one. This is 0.3 meter length. The diameter is, I think, 12 millimeter. Name selection. So this is my inlet. That the other side is my outlet, and this is the wall. That's it. So press mesh and update. So after that, let's go to Fluent. So let's see. Okay, so the way I'm trying to implement the boundary condition is using a UDF function. So what I want to apply is a temperature condition which changes along the wall of the tube. Okay, so just a steady state flow solver, because I'm not going to run any simulation. Turn on the energy equation and then specify your viscous model based on Reynolds number of the flow coming in. Now the key thing in this one is how to implement a boundary condition. For example, if I go to boundary condition and I already specified the inlet boundary condition as 1 millimeter per second velocity inlet, I specified the hydraulic diameter, and the thermal condition, the temperature is 300 Kelvin. So this is the fluid coming in. Outlet is just a pressure outlet, and the wall condition is going to be different. So I'll show you the constant one first. So constant thermal boundary condition. So let's say the temperature is a constant, 400 Kelvin. Click apply, initialize. Okay, and let's see, and go to graphics. After initializing, the boundary condition is already applied. So I want to see the temperature counter at the wall, and you can check out that the counter temperature is at 400 Kelvin on all over the surface. Now what if I want to apply variable temperature profile? Because imagine sun is at the top of this tube, so temperature would be different. Like at bottom it would be lowest temperature, at the top it would be highest temperature. Or imagine you have a parabolic throw at the bottom, or imagine this is a concentrating solar power collector, so heat flux would be different along the surface of the wall. So how to apply those things? Okay, so this is the UDF I wrote to apply that. Now there are two ways to implement UDF, but let me explain the UDF first. So you have to put this one, include udf.h, define profile. So we are going to apply the boundary condition with a profile boundary condition. TT wall, this is the name that you will see when you select the boundary condition in here. This is thread, this is position. So we are going to apply the boundary condition not based on time but based on position. Okay, position like x, y, and z coordinate on the walls. Okay, so real z, now this z can be x, y, z, a, b, c, d, whatever. Okay, so what it is doing is it is assigning this variable and importing all the coordinate points. So nd underscore nd means so nd is like I forgot the what this one completely means, but if you change this value like the underscore nd, so this is going to be 3 dimensions. I think it's the number of dimensions. So if you put 0, that is only going to store the x coordinate points. Okay, only going to store the x coordinate points. So x coordinate points along these values. If you put 1, this is going to be y coordinate point. If you put 2, this is going to be z coordinate point. So we have only 3 coordinates in here. If it's only 2 coordinates, then you can only apply 0 and 1. Okay, so this problem has 3 coordinate points, x, y, and z. So either 0, 1, 2. Phase is like the elements you saw. So imagine, actually should have created. So imagine, let me open the mesh. That might be good. Okay, give me 1 second. Okay, well, while it's opening up, let me, okay, it's up. So you see the mesh. Let me look at the inlet. And so what you see in here is the elements. So I'm trying to apply the boundary condition at the inlet. So you see these corners. So let's say this is the element, and this side, which is open like at the wall, that's my face. Let's say, okay, face of this cell. Okay, this one is the face of that cell. This is the face of the other cell. Okay, so we have all these faces. Okay, so here is I'm assigning face underscore the thread as a variable f. Okay, and these are some real values instead of integer. These are real values, the constant values I'm going to use. So Q max, Q min. Basically, I'm actually using temperature, so I should have used T max, T min, but you can also apply heat flux as well, similar way. So it doesn't matter. So Q max, Q min, D is my diameter, which I didn't use in here. Radius I also didn't use, so you can ignore those things. Z max is my Z coordinate point. So you see this X, Z. X is along the length, Z is along this direction. So Z is from, the way I created my geometry is the middle point is 0, the left point is negative value, the right point is positive value. So you can also go to Fluent and go to General and click check. So that also gives you the maximum minimum coordinate value. So you can see Z coordinate value is 6 millimeter, maximum value is minimum value is negative 6 millimeter, maximum value is positive 6 millimeter. Okay, so what I'm trying to do in here is so I specified what's the maximum value for Z because I'm going to use that in my function, and I started a for loop, okay, with the face and going through the face and the threads. Okay, thread is multiple faces creates a thread. Okay, so because I want to apply those temperature boundary condition on the faces, because that's my wall surface. Okay, all the faces merged together makes the wall surface. Okay, if centroid, what it does is this is the subroutine from Fluent. What this one does is this one gets the value at the center. Okay, so what is the centroid position of the elements? Okay, so this is what this does. So centroid of, now this is not the Z coordinate, this is basically like whichever variable you're taking. Okay, now because we are just getting the centroid, so whichever surface we are applying this UDF to, that's going to be that coordinate. So if it's x coordinate, this is the y coordinate, this is the coordinate domains. This is the phase, this is the thread. Now we are going to apply the profile. So this is the main line. Okay, this is the main function. So we are applying with f profiles. Again, these are all Fluent subroutine. If you want more detail, you can Google it. Now f is the face, so I'm going to apply this profile to the faces and the threads of those traces and in the positions. Now now I'm going to apply this boundary condition on each of the element faces, like this face, this face, this face. Like in this case, it would be this face, this face, this face, this face in all the faces on this wall. Okay. So how am I applying it? Let's see. I'm specifying Q mean. So I want to again, this is temperature, so don't get confused. This can be any kind of boundary condition. So this is my minimum temperature. Let's say this is the difference between the temperatures. So this is my delta Q. Okay. Again, delta Q plus Q mean is basically Q max, right? So Q max minus Q mean times this cosine theta. So what I want to apply is, let's say this side is maximum temperature, the other side is minimum temperature, and the middle points are going to be some interpolation points. Okay, the temperature is going to gradually increase, and on the left side this is minimum temperature, on the right side is maximum temperature. Same will go with the bottom one as well. Okay, so how can we do that? Let's see. This is there, so I assign the delta Q. Now when cosine value is 0, then this one becomes 1. Okay, and Q max and Q, so basically if this value is 1, this is just Q max minus Q min, so it would be the maximum value, so delta Q. Okay, delta Q plus Q min would be Q max. So so the way we want to apply the boundary condition is whenever we are at the opposite side, so Z is in here, so let's see, Z. Okay, so if you are in this location, okay, then this should be Q max. Okay, and if we are in this location, this should be Q min, and it's going to gradually increase. Okay, Z coordinate points. So this is what I applied. So Z cosine theta 90° times Z max minus this Z1. You see, I have put 1 in here. This 1 means this is going to take 0, 1. So this is going to take Y coordinate points. So basically what I'm using is Y coordinate points to apply the boundary condition. Again, you can put 2 as well. So it is going to take Z coordinate points, and this one is pretty symmetric along Y and Z, so it's going to be same. But if you put 0 in here, okay, the boundary condition that's going to be applied is along the length. So temperature variation would be along the length. Okay, but if you put 1 or 2, it's going to be along the diameter. Okay, along the perimeter. Okay, so let's try it out. So I've already saved this one. Now, there are 2 ways to load UDF. One is interpret, another one is compiling, like creating a library. What's the difference? The difference is, so just go to user define functions, and there are interpreted option, there are compiled option. Interpreted is you directly use that UDF. Okay, so just browse it wherever that is. So this is my file, walltemperature.c. and I'm going to click interpret, and there should not be any error. It has interpreted properly. And if you go over there now in the boundary condition of the wall, you can see I have this TT wall 2. Remember, I say this name is going to be there, so this is the TT wall 2. And so instead of constant, I'm going to use this boundary condition, click apply, and initialize again, and see how the boundary condition changes being applied on the wall. Now, one other thing is what would be the difference between interpreted and compiled? So compiled, they does the same thing. They create the same type of boundary condition. The major difference is an interpreted UDF would be loaded in each iteration, but a compiled UDF would be for throughout the whole simulation. So compiled is whenever you run a big case, usually it's a good practice to compile it and then use it, because that would create a library for it, and you don't have to load the UDF in each iteration, because that would slow down your total computational time. Okay, so you can test it out with interpreted, but when you run it for the final time, do compilation and then run your case. Okay, so let's take a look at the wall temperature, and you can see my range. 300 is there because my initial temperature is 300, so here is actually the 300 range somewhere in here there. But however, on the wall the range is in between 400 and 480. We can check it out. So definitely the maximum temperature is 480, and you can see it over here. And if you go down, so this is the lowest temperature. If you right click, you see it's around this range, 400. So I think I should be able to find a 400 value in here if I check through it very thoroughly. So this is how you can implement the boundary condition, like variable boundary condition along the perimeter. But how about if I want to apply it, change it along the length? So all you need to change is, let's say instead of z equals 1, I want to use the variable as an x variable. Okay, and certainly you should actually specify the maximum x length as well, but let's go with that. The number would be different, but the rate of change should be there. So let's try it out and see. So I've saved it. Again, I'm going to interpret it again. Okay, it's already over there, so it has interpreted again. I don't have to select it, it's already selected, and I have to initialize again. Okay, so let's display it. So again, that Z max value burned this one. So the maximum X length should be, so it's actually repeating 0.6 meter, 0.6 meter, 0.6 meter, 0.6 meter, and from hot to cold, hot to cold, hot to cold, hot to cold. Okay, so basically I just have to change this value to fix this one. So this one should be my X max because I'm using X coordinate. But you got my point that you can actually change your temperature along the X length as well as along the Y and Z coordinate points as well, like along the perimeter. Okay, so this is really helpful when you're trying to do any solar heat flux, or like I'm showing you the temperature, but you can just select heat flux and apply the same condition, because these are all just numbers. These are just going to give it numbers. Like you can specify, if it's a heat flux, you can specify from Q min is 0, Q max is maybe 40,000 watt per meter square, and then apply the same function to apply it however you see fit. Okay, this helps a lot, and this reduces the computational time by a lot when you are actually doing a solar receiver, tubular solar receiver type of simulation. I hope this helps. So after that, it's just regular old simulation. Go to the run calculation if you want to do a steady state, then do a steady state problem. If you want to do a transient, then do a transient problem. I hope this helps everyone. Thank you.